Commonly available cable sizes for aluminum include 250 kc mil, 300 kc mil, 400 kc mil, 500 kc mil, and 600 kc mil. For copper cables, commonly available sizes are 250 kc mil, 300 kc mil, 400 kc mil, 500 kc mil, 600 kc mil, and 750 kc mil. Although 600 kc mil is commonly available, it is less common than other sizes and may be more difficult to obtain in some areas. Electricians generally prefer parallel conductors for cables above 750 kc mil because this allows for easier installation and bending, especially in tight spaces. 750 kc mil cable is relatively rare. Electricians may not prefer to work with 750 kc mil cable because it is not as readily available and can be more challenging to handle. When considering parallel conductors, the number of parallel conductors will depend on the required ampacity. Each conductor should be installed in a separate conduit or cable tray to prevent overheating and electromagnetic interference. The electrical code does not specify a maximum size for cable. However, the practical limits are determined by the availability of materials, the ability to handle and install the cable, and the voltage and ampacity requirements of the system. In general, cables larger than 1000 kc mil are rare and require specialized equipment for installation. Common cable sizes for both aluminum and copper range from 250 kc mil to 600 kc mil. For cables above 750 kc mil, parallel conductors are generally preferred by electricians. 750 kc mil cable is relatively rare and may not be readily available. The electrical code does not specify a maximum cable size, but practical limits exist based on availability, handling, and voltage and ampacity requirements. When selecting cable sizes, it is important to consider several factors. Firstly, determine the required ampacity for the circuit. This is the amount of current the cable needs to safely carry. Consult the National Electrical Code, specifically Table 310.15. B16 or other relevant tables for ampacity ratings based on conductor type, insulation, and installation method. Secondly, consider the voltage drop. Longer cable runs can experience significant voltage drop, which can affect the performance of connected equipment. Use voltage drop calculators or consult engineering tables to ensure the voltage drop remains within acceptable limits, typically no more than 3% for feeders and 5% for branch circuits. Thirdly, evaluate the installation environment. Factors such as ambient temperature, exposure to moisture, and the presence of corrosive substances can impact cable selection. Choose cables with appropriate insulation and jacketing materials to withstand the specific environmental conditions. Fourthly, assess the available space. Confined spaces may limit the size and number of cables that can be installed. Parallel conductors can be a practical solution in such situations, but ensure compliance with code requirements for proper spacing and termination. Fifthly, take into account the cost and availability. Larger cable sizes and parallel conductor configurations can be more expensive and may have longer lead times. Balance the cost with the performance and reliability requirements of the system. Sixthly, ensure proper termination and splicing techniques are used. Incorrect terminations can lead to overheating, voltage drop, and potential safety hazards. Use appropriate connectors and follow manufacturer's instructions for proper installation. Seventhly, adhere to all applicable codes and standards. The National Electrical Code and local building codes provide detailed requirements for cable selection, installation, and protection. Comply with these regulations to ensure a safe and compliant electrical system. When installing parallel conductors, several specific requirements must be followed to ensure safety and proper operation. Firstly, all parallel conductors must be the same length. Differences in length can lead to unequal current distribution, potentially overloading some conductors and causing overheating. Secondly, parallel conductors must have the same conductor material. Mixing copper and aluminum conductors in parallel is not permitted due to differences in conductivity and thermal expansion characteristics. Thirdly, parallel conductors must have the same size and circular mill area. Using different sizes can also lead to unequal current distribution and potential overloading. Fourthly, parallel conductors must have the same insulation type. Different insulation types may have different temperature ratings and dielectric strengths, which can affect the overall performance and safety of the installation. Fifthly, all parallel conductors must be terminated in the same manner. Use the same type of connectors and follow the same installation procedures for all conductors to ensure consistent and reliable connections. Sixthly, the overcurrent protection device must be sized to protect the smallest conductor in the parallel set. This ensures that all conductors are adequately protected against overloads and short circuits. Seventhly, the equipment grounding conductor must be sized based on the total ampacity of the parallel conductors. Refer to the National Electrical Code Table 250.122 for proper sizing of the equipment grounding conductor. Eighthly, parallel conductors must be grouped together. This helps to minimize inductive reactance and ensure proper current sharing. Grouping can be achieved by using cable ties, straps, or other suitable methods. Ninthly, each parallel conductor must be identified at both ends. This helps to ensure that the correct conductors are connected together and simplifies troubleshooting. Tenthly, consider using a derating factor if multiple parallel conductor sets are installed in close proximity. Heat from adjacent conductors can reduce the ampacity of the conductors, requiring a derating factor to be applied. Consult the National Electrical Code for specific derating requirements. For example, if you have a requirement for 800 amps, you could use 2 sets of 500 kc mil copper conductors in parallel. Each 500 kc mil copper conductor, with a 75 degrees Celsius insulation rating, is typically rated for 380 amps according to NEC Table 310.15. V16. 2 sets would provide 760 amps. You would need to verify this with the equipment terminations to ensure they are rated to accept 2 conductors. You may need to increase the size of the conductors to accommodate voltage drop. This is a very important consideration in any electrical design. Use industry standard voltage drop calculators or software to properly size the conductors. The National Electrical Code provides guidelines for voltage drop in Informational Note Number 1 to Section 210.19. A1 for branch circuits and Informational Note Number 4 to Section 215.2. A1 for feeders. These notes recommend a maximum voltage drop of 3% for branch circuits and 5% for feeders. These are recommendations and are not requirements. However, it is considered good engineering practice to keep the voltage drop within these limits. You should also consider future load growth. If you anticipate that the load will increase in the future, you should size the conductors to accommodate the future load. This will prevent you from having to replace the conductors later on. For example, if you have a 200 amp panel and you anticipate that the load will increase to 250 amps in the future, you should install 300 amp conductors. Another consideration is the type of equipment being served. Some equipment, such as motors, requires larger conductors to handle the inrush current. The National Electrical Code provides guidelines for sizing conductors for motors in Article 430. For example, the conductors supplying a single motor must have an ampacity of not less than 125% of the motor's full load current rating. Always consult with a qualified electrical engineer or electrician to ensure that the conductors are properly sized and installed. Improperly sized conductors can lead to overheating, voltage drop, and potential safety hazards. Here is some more information about ampacity derating. Ampacity derating is the process of reducing the allowable current carrying capacity of a conductor based on certain conditions. This is done to prevent the conductor from overheating and potentially causing a fire. There are several factors that can cause ampacity derating, including ambient temperature, the number of conductors in a raceway or cable, and the presence of other heat-generating equipment. Firstly, ambient temperature. The ampacity of a conductor is based on a specific ambient temperature, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than this, the ampacity of the conductor must be derated. The National Electrical Code Table 310.15 B2 I provides ampacity correction factors for different ambient temperatures. Secondly, number of conductors in a raceway or cable. When multiple current-carrying conductors are installed in the same raceway or cable, the heat generated by each conductor can raise the temperature of the other conductors. This requires the ampacity of the conductors to be derated. The National Electrical Code Table 310.15 B3 I provides ampacity adjustment factors for different numbers of current-carrying conductors in a raceway or cable. Thirdly, presence of other heat-generating equipment. If a conductor is installed near other heat-generating equipment, such as transformers or lighting fixtures, the heat from this equipment can raise the temperature of the conductor, requiring the ampacity of the conductor to be derated. The amount of derating required will depend on the specific situation. To determine the appropriate ampacity derating factors, consult the National Electrical Code and other relevant standards. The ampacity of a conductor is the maximum amount of current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor is determined by several factors, including the conductor material, the conductor size, the conductor insulation, the ambient temperature, and the number of conductors in a raceway or cable. Firstly, conductor material. Copper conductors have a higher ampacity than aluminum conductors of the same size. This is because copper is a better conductor of electricity than aluminum. Secondly, conductor size. Larger conductors have a higher ampacity than smaller conductors. This is because larger conductors have a greater surface area to dissipate heat. Thirdly, conductor insulation. The type of insulation used on a conductor affects its ampacity. Some insulation types are better at dissipating heat than others. Fourthly, ambient temperature. The ampacity of a conductor decreases as the ambient temperature increases. This is because the conductor has less ability to dissipate heat when the ambient temperature is high. Fifthly, number of conductors in a raceway or cable. When multiple current-carrying conductors are installed in the same raceway or cable, the heat generated by each conductor can raise the temperature of the other conductors. This reduces the ampacity of the conductors.